Mic seems to be working well. Thank you for the invitation. I'm very happy to be back, Intel, Verizon, now Verizon, and present to this group and to the South Bay area in general. I'm a bit jet-lagged. I just arrived last night, so if I'm sort of kind of dizzy, then please excuse that. You have to keep me awake, let's put it that way. Good. So what I'm gonna talk about is a more specific thing about binary compatibility, and I'm gonna say more about that and how it relates to other things in my keynote at Scala Days on Monday. So here is sort of one deep plunge into a fairly technical subject, and it's about binary compatibility. And it's a subject that is sometimes quite painful to talk about, so we definitely wear a little bit the hair shirt when it comes to binary compatibility. Let me maybe ask you, who has already had a problem upgrading to a new version because of binary compatibility problems? Well, quite a few, yeah. We often, the Scala community or TypeSafe or EPFL gets accused of not taking the problem seriously enough, it's a matter of discipline. We're just not disciplined enough. People just change their code all the time and it breaks all the time, so it must be somebody's fault, right? What I try to do in this work is to analyze this a little bit. Where do these problems come from? And then also maybe to point out the solution, what we can do about it. So the problem in a nutshell has been that, it's been an issue with the Scala community for a long time, since its beginning, since it became popular. And the early problems were that things broke left and right, and the community has learned to deal with it to a degree by becoming more conservative. And becoming more conservative means changing less often, and it also means, I think, having fewer dependencies. You hear it a lot about this idea of zero dependencies, and I think that by itself is a problem. It means that we can't reuse code of others as well as we could if we had more dependencies, or use dependencies more freely, but then right now we run into these binary compatibility problems. So it's a bit of a problem. The dilemma here is, well, you can either innovate and break your client's builds, or you freeze and stop improving. And that's sitting between a rock and a hard stone. So the question is there not a third way that we can do better? So let's analyze first what binary incompatibility is, because I think even though many people have been burned by it, probably few people had the patience to really go down and say, well, what was the reason why this library doesn't work in the newer version yet? So to put it in a nutshell, here's a problem where you have a source and binary incompatibility. So you have a client object, and it uses a server, and in the server you have a message, and it's just a string, and then you decide, well, message should really become an option, because you don't want to use nulls, which is very reasonable. But if you do that, then of course that thing here won't compile anymore, because you can't take length from an object, and it won't be binary compatible, because essentially the bits don't agree. So we all agree that that's something nobody can do anything about, except if we put some artificial intelligence into our sort of programming upgrading tools, which is a fascinating idea and fascinating project, but maybe not right there yet for tomorrow. So here's a thing which is source incompatible, but it's actually binary compatible. So we have a client object, and it imports two objects, A and B, and it has, we do a very clever thing. We assign one to a string, and that works because we have this beautiful implicit conversion which makes us pretend that we can do actually JavaScript-like things. Great. Only now somebody comes and says, well, I have a great idea. Let's just do this just twice as good and have another implicit conversion that also goes from int to strings, but this time it is just a fixed string, ABC, like this one here. So If we do that, then of course our program won't compile anymore because the implicit conversions are ambiguous. There are two now that imply. But if you look at the bits, at the bits in the class files, they don't care because the implicit conversion has been resolved. So these things will continue to run until you recompile, in which case you will start to notice the problem. Okay, so let's now go to the one which is sort of the real problem, something that's source compatible but binary incompatible. So here we have an object, call it Apple. It extends edible, and it has a jowls field or a method. Edible is a trait with the abstract method jowls. And now we say, well, actually, it would be nice to also have a calories method, which is just jowls by 4.184. And that's just a convenience method that we add to the trait. If we do that, then until, for all current Scalas, you need to recompile. Why do you need to recompile? Well, if you look at the implementation of this trait, then that's what it looks like. So a trait becomes essentially just an interface in Java. I'm continuing to use Scala syntax, but I now sort of restrict myself to what I can do with Java interfaces. So two abstract methods, jowls and calories. And the calories method, because I already have an implementation, I write this into a so-called implementation class, which comes with the trait in the class file format that Scala compiles to. And now in the client, so in the Apple object where I implement the edible interface, I essentially have a stub for this method that forwards to my implementation class. So in the implementing classes, I fix out the methods that the traits define. Okay, so now the problem, of course, is that if I do that, then initially I only had an interface that use jowls like this, and now when I add the calories method here, I need to add it also to the implementation of the implementing class, which is something that the compiler adds for me. So if I don't recompile this thing, then that method will be missing, and I will get an error that essentially I have an abstract method error in the JVM, which says the method calories wasn't implemented by this object. So that's a problem in principle that had to do with the way we implemented mixins, and there's no other good way to do it. And that couldn't be solved until Java 8. So Java 1.2.7, essentially, that's just something we had to live with. With Java 8, it's slightly better. So in this example, one could say, well, Java 8 has default methods in traits. So now we could actually declare this thing a default method, and we would actually solve this problem here. And Scala 2.12 will do precisely that. So it will use the default methods of Java 8 to solve that. But it's essentially a solution that is just one step. So as soon as you have several methods that can implement a thing, so you have conflicting possibilities in traits that you inherit, or as soon as you add vals or vars to your traits, the whole thing breaks down and you have to do the same thing again. So it's sort of, in practice, it will help you with some of the binary incompatibility problems, but by far not with all of them. And that's only talking as far as traits are involved, and there are, of course, a lot of other issues as well. So here's another one. Let's say we want to say, well, our calories implementation is, of course, terribly expensive. Multiplications are, let's pretend multiplications cost us millions of cycles, so we want to cache it in a lazy val. So if we do this, then the compiler has to work a little bit harder, because lazy vals, they have this evaluate once semantics. So you evaluate the first time you call it, and then you want to cache the results. So the way it's done is that there's a hidden var that essentially stores the value of the calories, and then essentially there's a flag, there's a bit in a bit set that tells you whether you have have already computed the value of the calories, and in which case you can simply return it directly, and otherwise you have to compute it and store it in the variable. So that's the scheme of lazy values that we have in Scala. But it turns out that it's actually lacking. So we spend 1 bit per lazy vals, and it turns out that there are some situations where you can run into a deadlock just because of this lazy val scheme. Basically, what happens is in a multi-threaded context, essentially you take the lazy val, you find out you have to recompute the value, you lock the object to say, well, while I recompute the value, I lock the object so that nobody else can implement this lazy val, and essentially once the initializer has run, I can come back. The problem is that locking the object, of course, can interfere in bad ways with locking schemes that other people use. Somebody might need to lock the same objects, or worse, you might have 2 lazy vals and you have 2 threads. Each one of them grabs a lazy val and says, I need to initialize that, and then each lazy val needs the other to be initialized. Then you have another problem here. So it turns out that actually these problems can be overcome if we spend 2 bits per lazy val, where essentially the first bit says, essentially the 2 bits encode a little state machine that says, well, hasn't been touched yet, or is currently about to be initialized, or is fully initialized. Because then you could say, well, if I do that, I only mark the variable as is about to be initialized. Then another thread comes and says, oops, somebody's already working on this, so let's just suspend and be notified by the other thread when the other thread is done. And finally, if the thread comes back and says, well, there's actually more than 1 thread that wanted the variable, I notify everybody else. So that scheme can be made about as efficient as the current one. It spends 2 bits, so it's a clear, that's not a big overhead. So it's a clear win to do it this way. The problem, of course, is if you do that, then all your bit layout of all your data changes, and that's another big problem with binary compatibility. You have to recompile everything, so it's a big disruption to do this. We can't just roll this change into a build release, into a patch release, because, well, everybody would have to recompile. And that's, again, just a thing to say, well, nobody's perfect, so we cannot assume that the Scala compiler from 10 years ago should do exactly the same algorithms and things as the Scala compiler now. And the Scala compiler 10 years from now will again use different algorithms. And I think the world works like this. You wouldn't expect a hotspot VM to have the same JIT compilation as 10 years from now. And 10 years in the future, it will again be different. So because Scala, the binary format, was so much out in the open, we had been restricted in ways which are really extremely severe because of this problem. So if you look at what goes on in a compiler, then that's just a little snapshot of a current compiler pipeline. And you see there's actually a lot of things that a Scala compiler has to do until it can eliminate it can spit out Java bytecodes. So there's a front end, which you see here up there. There's a typer, first a parser that essentially parses source, produces syntax trees. Then there's a typer, which essentially adds the types to the syntax trees. Then there's a phase that adds synthetic methods, so like the equals and the hash code for a case class. Then there's a super accessor methods, which is quite obscure what it does, but important. And then there are lots and lots of other phases. So that one eliminates repeated parameters, so var arguments. That one adds extension methods for value classes. That one makes methods tail recursive. That's a pattern matcher. That one adds explicit outer pointers for inner classes. That one is lambda lift that puts moves all methods to the top level, and so on. So each one of these does something that is interesting and quite substantial. And without having to go into details, I just wanted to sort of convey to you the impression, well, that's a lot of stuff. A lot can go wrong, or a lot can actually be wanting to change in future versions. So let's have a look at how that affects binary compatibility. So where it breaks is very simple. You have a client, A, and it uses a library class C, and you'd have a binary incompatible source change. So then you get a new class. And of course, if you use the previous clients with the new class, then because it's binary incompatibility, it will break. So that's, in a nutshell, that's what people observe. So why is that such a painful problem? It seems to be a rather simple and trivial thing. So here's one of the bad scenarios. So you have your shiny new application, and as things happen, it relies on some dusty legacy library. It was hot at some point, but then people have long moved on, and this thing is forgotten, but it's still in your build, and you still rely on it, and it works. So there's no problem. And this dusty legacy library relies on an ancient version of Scala, let's say 2.10. So now into 2.10, we want to do it much better. So we have a new version of, let's say, a class in 2.10 I just pick sequence, and we have a binary incompatible source change in 2.11. Okay, so no problem. My application is still very much active. I just recompile it, right? No, because our dusty legacy library is too old. We can't rebuild it. Nobody even knows how to build this thing anymore. We just have the jar somewhere, right? So that means that, no, you can't migrate your application because it relies on this thing, and you can't migrate this dusty legacy library because you don't know how to build it. And that's sort of a problem that initially you probably can discount, and it won't be important, but in a big company, in a big organization, the bigger things become, and the longer they live, the more likely this scenario is. Okay, and that's actually not just a problem for Scala. It's a problem for essentially every system with components. So we were talking here about the Scala library, but nothing is specific for the Scala library. We could talk just as well about Akka, or we could talk about Shapeless, or any of the other commonly used Scala libraries. If they have a new version, which is binary incompatible, then anybody relying on those versions will have the same problematic failure scenarios. Okay, so what's been done to deal with this problem so far? It's not nothing. In fact, people have been working quite hard on that. So the first thing that we did was we had this tool, at least to say, well, we want to detect binary incompatibilities. Not only in deployment, when you deploy this thing and it doesn't work, but we want to detect it before that. So we want to be able to say, if we have a jar and we do some changes to the jar, some bug fixes, is the new jar binary incompatible or not? Previously, the only answer was, well, try it out and see whether something breaks. So now we have a tool that actually, since quite a while already, we have a tool that detects this. It's called MIMA for Migration Manager, and it can verify whether things are binary compatible or not. And then with that, you can implement a policy, and the policy we currently have is that minor versions of Scala and the Scala library must be binary compatible, forwards and backwards binary compatible. For major versions, we are allowed to break them, but major versions are the release cycle for major versions has already slowed down a bit, and probably will slow down further a bit. So it's currently at about 18 months. So it gives people some time to actually adapt to not be overwhelmed by all these changes. But the problem is that that only applies so far to the Scala standard library, but third-party libraries need similar policies, but often they don't enforce them yet, and if they would, and they will at some point probably, then it's the same problem we already face now with the Scala standard library, that innovation is stifled. Simple fixes have a long time to get in, and also what I notice with our developers, a lot of cycles are spent on dealing with binary compatibility. I see when we get a patch, let's say, to the Scala standard library, then it's one thing to say, well, we do the fix, and it often takes at least the same amount of time, if not more time, to say, well, what are the ramifications for binary compatibility? When exactly can we schedule this change, and so on. So a lot of effort is spent on this problem. So that makes you ask, well, if we all spend such a lot of effort for overall not that great a result, so what do others do? Let's have a look what the situation in other language ecosystems is. So let's look first at our cousin Java. So Java has the advantage that it's very close to JVM bytecode. So if things change, they typically change at the JVM level. So major changes are reflected by changes on the JVM level. Take lambdas, for instance, that use essentially new bytecode instructions for invoke dynamic. Or take default methods. That's again something that the JVM will simply support. The other thing is that because the bytecode format is kept very stable and innovation often happens underneath, that is sort of mirrored by an attitude in the community to say we want to keep the bytecode files, the Java bytecode files, very, very stable, even if it means keeping completely non-working and outdated things like Java util alive, Java util data alive for a very long time. Everybody knows it's broken, but nobody gets rid of it because people just value binary compatibility very, very highly. And I think that's quite a rational attitude here. And the language, Java itself, is quite restricted in terms of extensibility. So until default methods, for instance, you needed to have for each new version of an interface in Eclipse, you made a new interface, and then the client had to deal with all these things. So the language sort of gives you a fairly rigid structure in which you can live, and it sacrifices to some degree the extensibility of the language and the architecture for the sake of binary compatibility. And that makes it work quite well. Another way to go on the Java side would be OSGI. So OSGI is actually quite interesting take on binary compatibility. So if this whole thing were running in OSGI, you would have a different possibility. So you would still have your Dusty legacy library. You would still upgrade the Scala library. But now you could just rebuild the application and keep this thing in its own class loader, and that class loader for Dusty legacy library could have a version of Scala library 2.10, whereas your application would have migrated to 2.11, and the two could coexist. So that's the theory. In practice, it's quite fragile because you have two versions of everything then here, and they, at the interfaces, they have to sort of talk to each other, and that can become quite a hassle. So in practice, very few frameworks have actually bought into that concept. The best known is Eclipse, but it hasn't spread that far further than Eclipse. So what about C++? Well, it relies on a linker for more flexibility of interfaces, but I think generally it's not that great a story either, so the name DLL hell doesn't come from nothing. What about Clojure? Well, Clojure builds from source. I don't have a problem there, right? So no binary compatibility because you ship stuff in source and you compile from source. What about JavaScript? JavaScript builds from source as well. There is no binary format. It's just JavaScript, right? Python builds from source as well. Ruby builds from source. Go builds from source. Yeah, so it seems like a lot of languages built from source. And of course, then if you build from source, you don't have a problem of binary compatibility. You might have other problems, but definitely not binary compatibility because it's all just source. So why can't Scala build from source? Isn't that something we should consider? Well, we have a couple of problems here. The first one is in the other languages, you typically have a standard build tool or deployment tool. In Scala, we don't have that. We would have to pick a winner here among SPT or Gradle or Maven, Ivy, and it's just too fragmented. You will never be able to pick a standard build tool and say, well, everybody uses that build tool. Even then, the build tools are very, very flexible, and builds are very, very reproducible builds are very, very rare. So everybody has their own concoction of how to actually build this stuff, and it's quite a rocket science or magic to actually build this stuff, so it's very, very hard to reproduce. And to some degree, it's a chicken and egg problem. Because everybody is used to binary builds, nobody invests in making builds reproducible. Because that's not the problem, you ship the binaries, right? Whereas, let's say if I pick Go as an example where you build from source, well, you probably wouldn't do some exotic acrobatics for your build because you say, well, I can never reproduce that. But because the Scala community has grown up essentially with this idea to say, well, our build system is built around Maven, so everything is binary, the problem never was looked at, and now it's too late, of course. Now it's not possible to get reproducible builds again. Well, nobody invests in making builds reproducible. It's actually not quite true because TypeSafe has invested a lot in the community build, and we now can build more than 1 million lines of community projects with essentially every night, with every release of Scala, we actually check that all these projects build. So, but that's essentially just what one company does, and the total code base of Scala exceeds this thing by several orders of magnitude. So this is just one effort, and it was quite a big effort to have this working. So what we need would be then, and what I'm going to propose is to have an interchange format instead of bytecode that should capture the essence of Scala dependencies. So that can't be the JVM bytecode format, what it is now, because we've seen that causes us all these problems with binary compatibility. And it can't be source because we can't get reproducible source. So we need something different, something independent of what we have seen so far, and also independent of Java bytecode. So the idea there is then to say, well, what could be a good format for that? And what has come out, what has sort of emerged there is that we should be able to use trees, the abstract syntax trees, together with the types of those trees. So use type trees as the interchange format. So I'm going to show you that this is much more robust than source. And so in particular, it should be easy to get reproducible builds with that. And it's much more stable than JVM bytecode. So it will essentially take care of all the binary compatibility problems, or at least the major classes of binary incompatibility problems that we see there. And I'm also going to argue that it's efficient. So the new compiler idea pipeline would be to say, well, let's snip off the front end, which is essentially parser, typer, and then maybe some number of phases that don't do much. So essentially, immediately after typer, we snip it off. And we produce these typed trees, these typed ASTs. And we can then feed the typed ASTs to the rest of the compiler. And the standard compiler would just go from one to the other, and the typed trees would essentially be produced on the side. You could say that's nothing new, because that's what the Scala compiler does anyway. So at this point, essentially, it dumps the symbol table. It dumps all the symbol definitions in a file into an annotation that it ships with the class files. And it needs that to actually figure out what's in other Scala files so that it can do separate compilation. So that's what we do already anyway. So the only change here would be that instead of dumping the symbol table, we dump the whole AST, the whole tree with symbols, well, with the definitions of symbols, with them, but also with the bodies of methods, with everything. And the normal compilation pipeline would then immediately go through the backend and produce bytecode. But the idea would be that you could actually come back and take these type trees and run the backend again without running the front end. So that's the advantage of this separation. So how would that affect our builds? So the idea now is that if I have this application, and then let's say that's the Dusty legacy library, and that's my class C, then together with the class files, I would ship the tree, the full syntax tree, and I also would ship essentially a hash that tells me what is in the class file and the tree. So I recompile that with a source change. I get a new class with a new tree and a new hash. And then I say I want to rebuild my A.Scala, and I would then have to look at the dependencies and say, okay, it relies on the B class, and the B class has in its hash essentially all its dependencies. So the hash of C is included in the hash of B. And now we say, well, if we take the new things we have, is it still the same hash? It wouldn't be, because that hash has changed. So we would know that we have to rebuild the class B. And that would be done from the tree of B. So we don't have to have the source of B. We have the tree of B, and we can immediately run essentially the back end of the pipeline to produce new class files. And once we've done that, we are in a position to apply the same thing to A, and everything is over on the new side. And it's all done automatic without having to look at build scripts or manual recompiles. OK, so how is this better than going from source? It looks like if I would just take the sources, I could do the same thing. And that's true, but like I said, a lot of sources actually quite a subtle thing. So if we look at what happens in this typer thing, so the front end, then a lot of tricky things happen. So the typer has to resolve names. It has to say, in particular, it has to say, well, I need to look at a class, a name that represents a class. I have to look at my class path and find out, well, what's the concrete definition of that class? If the class path on your client is different where you ship it, then you will have a problem here. It has to handle imports. It has to establish implicit scopes. If in your new project you have, let's say, you add an implicit definition or conversion somewhere, then you probably have realized that this can have a huge ripple effect on essentially everything in your build. It can cause ambiguous implicits. It can give you a different resolution of implicits or so on. So implicits are very, very subtle. So if implicits change and you just ship this thing with different implicits and say, well, recompile from source, but you can keep your fingers crossed that the new build will still work, but you can't give 100% assurance. I don't think you will be able to do that. OK, and there are lots of other things. Apply conversions, infer type parameters, assign type to trees. So a lot of these things can be very subtle to do. Overall, if I look at the current modern compiler, the new compiler we look at, which is much smaller than Scala C, this whole thing is about 5,500 lines. And, well, 5,500 lines can be quite a large source of errors. So whereas if we look at the backend, if we take the type trees, and actually the type trees, I have to reproduce the types of the interior nodes, because otherwise the types would become very, very big. But this assigned types thing has just 311 lines. So essentially to produce from the serialization format the full tree, once I've deserialized with the types, I need 311 lines. Much, much better. It's also more resilient than bytecodes, because with this new idea, I can add fields and methods to trades. I can add lazy vowels wherever I want. I can change the implementation technology of lazy vowels in any way I deem necessary, because all this happens after I have the tree. So after I have the tree, I can just say, well, I roll in a bug fix in a compiler. It uses 3 bits per lazy val, whatever. Then I can say, well, that just will affect the hashes, and everything will be recompiled. So I just have to do this. I can also add and remove implicits. I can add methods anywhere. I can change imports, again, without affecting the format. And all of these would be source incompatible. So it seems like with the type trees, we have this perfect spot in between where we say all the sort of things that can affect source one way, or well, either source or binary things one way or another. At this sort of focus point, they are largely eliminated. Then the question is, well, is it efficient? The first thing it would be, well, these trees, can't they become very, very big? Can we still deal with them? Because now we're talking about, let's say, rebuilding a system with 1 million lines of code in it. Automatically, when you build, and you could have ripple changes of incompatibilities with these hashes that force you to do that. So size of trees is an issue on disk and in memory, and also transformation time. So size of trees, initially, it looks like quite a challenge. So here's a simple expression, xs.filter greater or equal 0. And if you look at what the compiler makes of this, then that's roughly the tree that it produces. So each of these boxes is a node. So there are overall 16 nodes, and I haven't even counted the types yet. Typically, the types make it much, much bigger. So you say, OK, 16 nodes, take an average size of a node, let's say 32 bytes, 512 bytes total. Double that to include type info, so that would mean 16 bytes of source give you maybe 1 kilobytes tree. So factor 64 blow up. For a 1 million line system, you would have 30 megabytes source maybe, and 2 gigabyte trees. So that looks like a bit daunting. But in fact, if you look at it in practice, you can compactify it a lot. So here's the format that we currently have, this tasty. So that format represents the tree essentially in a nested form. And I won't go into the details of it. So essentially, it takes the tree and lays it out like this one. So it's overall, it's an apply method and apply node. And there's a select node. So where we say, well, we call this filter method that takes a signature. So it takes a function, it produces a list. And all these things overall, so these are bytes. So we end up at 36 bytes for this thing, which is twice the source that we started with. If we do some bigger programs where essentially the savings are much bigger, we get to about 50% to 75% of source size, which translates to less than a quarter of the class files we generate anyway. So less than a quarter of the class files that we have, we put into this thing, and that would replace something that we do already now, namely the simple table serialization. So it's essentially quite manageable to do it that way. Speed, so the transformation and bytecode generation amounts to about 60% of total compilation time, so definitely significant. We can speed this up by essentially refusing phases, reducing the fast type assigner, and building different files in parallel. Once we are essentially at the backend level, we have way more liberties to do that, and we can use incremental compilation. So I believe that we can make this fast enough to work well in practice. Speed is something that we haven't really tested yet, whereas the serialization format, so the gains in compactness, we actually have a working thing that achieves that. Okay, so that thing seems to work, and it can address the binary compatibility challenge. And it actually turns out that it has lots of other benefits as well. So once you have type trees, you have a great format for optimization, interprocedural analysis. You have precisely what you need to do things like aggressive inlining, dead code elimination, whole program analysis. You have also precisely what you need to do sort of linter tools like abide or Scala-centric versions of find bugs, or instrumentation. So if you, let's say, want to find out code coverage and things like that, all these trees give you a standard format where you can suck in things and interpret them on a very high level, much higher than bytecode, and much easier to consume than bytecode. And also, it gives you precisely what you need for portability, because these type trees now allow you to decouple essentially the fact of publishing a library to the question for which platform it will be published. So you can publish a library once and have it then automatically deployed on both JVM and JavaScript, for instance. And also, you will be able to have it deployed on new versions of JVM, because the JVM also, after a long period of essentially stability, where nothing much changed for 10 years, now the JVM is actually moving again. There was a big jump forward with Java 8, and more such jumps are planned. I mean, Java 9 adds modules, Java 10 might add specialization, and all these things are essentially, again, jumps very much like Java 8, so that it will become effectively a different platform to compile to. And that means that if you essentially can have a layer that is high level and stable, then you're not dependent anymore to what version of the JVM you compile to. Okay, so what I see is how we're going to migrate to this is, so the whole thing is essentially part of this new compiler framework, .c, which we are working on. And we now have the serialization and deserialization, but we're also working on getting the same front end for current Scala C. So the idea would be that we would at first have that as an alternative mid-end and back-end, that we could go into this tasty format and the compilation pipeline that I've shown you both from Scala C and from .e, and then use again the bytecode emitter would be shared between the two. And that over time, we could actually snip this thing off and have that as essentially the standard way Scala code is published. And Once that is the case, then encourage essentially the whole industry to move over to the new format and hopefully fix this binary compatibility problem for good that way. So in summary, binary compatibility is a highly knotty problem. To solve it, I think we need to move to something that resembles much more a platform. So the platform would, of course, build on top of hosts such as JVM.js and be as interoperable as it is now. But Scala interoperation would essentially be formulated at a higher level, at this level of type trees. And I've argued that this has lots of other benefits as well. So to find out more, I will have a talk that expands on that a little bit at Scala Days. And of course, I would also be happy to see many of you and discuss many of you at Scala Days. We have 3 days next week for doing that. And for now, I thank you for coming. Thank you.
Wow, everyone, thank you. So right now it's going to be question time. So does anybody have any questions?
So with this new distribution approach, how do you see the deployment going to happen? Will we always build one assembly jar, or will we somehow partition and they build this, distributed trees into separate components?
It's largely orthogonal to that. So the idea would be we will generate class. So on the JVM, we will generate class files as before, and the class files will have, instead of the so-called Scala signature annotation, which essentially gives you the symbol table, it would have the full tree. So for a user, initially there's nothing to see. So the tree just handles the separation, the separate compilation aspects like the signature annotation does now, but you can do much more and more with it. That means when you put this into a build tool like SBT, they would be aware of that. And they would say, well, I get a version from Maven which is incompatible with what I have. I can detect that with the hashes and essentially locally change your local copy in the caches to be compatible by recompiling. So that would be one scenario to do it. Another scenario might be to say, well, I could have a service and I could have essentially the right versions for all platforms, for all combinations on Maven. There would be a thing that compiles these things as they come along. I think one can imagine one or the other, and I'm not sure yet what will win. I personally think that the local caches idea is better because it doesn't lie on sort of rely on a critical failure point. But other people say, well, maybe it's be integrated with essentially the Maven Central or something like that. But whether you build a single jar or just leave class files or use, let's say, Java 9 modules is completely orthogonal to that. That's sort of the output format. Yes?
Yeah, might there be a way to, might there be a way to export these type trees to, for instance, use them in DSL development?
Yeah, absolutely. So I actually have, I sent to Dotty internals the link. There's a Google Doc that essentially is a specification of this tasty format. And the idea would be to really make that available as a platform like bytecode format, to say, well, if you want to like consume Scala modules or generate Scala modules, then that's how you would do it. And there could be tools that generate them which are different from the compiler. So for instance, I'm not sure whether DSLs would go directly to it, but one idea would, for instance, be staging. So staging is this essentially program specialization depending on one input, where right now we have the problem that if we do that, and I mean, at EPFL and Stanford, we had a big staging problem project that does this, or the companies like Huawei who are doing this now. The problem is when you do the staging, you need to generate, again, a program. And right now you would generate a Scala source, but of course that's fickle again because you have to be sure you have the right compilation options and things like that. So I think staging tools would generate these type trees and just serialize them and be done with it. And all sorts of program generations. Let's say code coverage. You want to instrument your code. You wouldn't generate source. You would generate this one. Yeah. Yeah. There was a question over here. Oh, take the one in the back first. Yeah, Tim. Yeah.
So I recall we first talked about Dotty a long time back now.
Yeah.
I recall. So like, how much of a prototype is it versus like how like real might Dotty actually be?
Well, we have the plan is to have something that we can release an alpha version, so full of bugs, no doubt, and things like that, by next Scala days, so the Amsterdam Scala days, which is in June. So that's the current plan here. Yeah, that we can do something. It is open source. It is on GitHub. It has quite a lot of activities. So we are very close to have a working backend. So essentially, this shared backend, which is the same as the Scala C backend, is taking life. It will be Java 8 only initially. There's initial work on a JavaScript backend, and the last thing I was doing was precisely the serialization format, so that we have that now, and that will give us essentially interoperability and separate compilation, and that's sort of the big things we needed to get in place to get there.
At what level does the tree stops? Like, how deep is the tree?
Sorry?
How deep is the tree? At what level?
How deep is it? Well, all the way to the leaves. So everything. There was this issue to say, well, maybe you don't, well, because of course the tree is source, you can get the source back. So maybe somebody doesn't want to ship the source. Should that be possible? And I think yes, it will be possible. So you can say, I will stop generating code at the method bodies because you don't need that for separate compilation. You say you will ship essentially the headers of the methods, which will give you the types. You need that for being able to call them, but the bodies you will essentially hide, and that will make the trees more compact, and of course you won't be able to see them. Well, you can always decompile the Java bytecode, I guess, but they are obfuscators and things. Yeah. Yeah.
My question is, how does it affect Scala clients, Java clients that use Scala libraries? So should they be compiled now with the Scala compiler?
Yeah. So essentially, for Java, nothing changes. So that means Scala can still call Java, and Java can call Scala as before, because we generate the same bytecode as before. But it's true that the Java client cannot profit from essentially the automatic binary compatibility upgrades. So essentially, if you do a binary incompatible change to a Scala library, then you will have to manually recompile the Java clients. There's nothing we can do there, I'm afraid.
So if my Java client depends on Scala library that they don't have access to the code of, can I recompile it from the syntax tree and recompile my Java with this new?
Yes. That's actually a thing. So if you have a build, no, I have to correct myself. If you have a build tool that essentially, can do the same thing, of course. Yeah. But right, yeah, no, you're right. Yeah, I was.
Where do macros fit in this picture? And if I change a macro, will I need the source to pick that up, or can I get away without that now?
You'll hear more about that also at Scala Days. So essentially, this has big ramifications for macros as well. So the idea is that macros would use the same trees for the expansion. And so macros is essentially code that expands code, right? So the first thing is, well, how can you essentially expand code that's in other compilation modules and compilation units? And it would use the trees for doing that. The other thing is that the macro to work, right now, for the macro to execute, we have to use Java reflection. So essentially, a macro is some Scala code that modifies code, and it's executed using Java reflection. So that means there's an invoke method to a reflective call to the macro code, and then the macro code will run. That has several problems. So the first problem is, because that is so, the macro must exists in a project that is already compiled before you can use it. Because if it's in the same project as yours, then the bytecode doesn't exist yet. You can't execute it. The second problem is a problem of security. Because you run arbitrary Java bytecodes reflectively, that macro could take forever. It could do very bad things to your code, but it could also just, out of like bugs or things like that, take forever or use infinite amount of memories and cause your compiler to crash. So one example which I saw there which really scared me was that the Play team had this great idea to say, well, we have a macro that when you compile a query, then it will immediately go out to the schema and validate the query against the schema and give you immediate feedback whether your query is valid according to the database schema you have. Great idea, right? But only the problem is that this was done on macro expansion time, and you should know that in an IDE, the compiler is run and macros are expanded on every keystroke. Well, those guys use Sublime or something like that, not Eclipse. So it meant that if you use that thing, that macro in an IDE, then it would be like molasses. On every key, it was a database request, so it would sort of come back with these things. So it shows that sort of having unlimited code running in macros is actually quite dangerous. Whereas what we want to do now is for these trees, we want to actually have an interpreter that would be the interpreter that interprets macros. And then we can bound the times, we can do all sorts of things. We can give it limited memory, you can have it run essentially in a fixed amount of time and stop it if it takes too long and so on. So that's what's in store for macros here. I think they will be overall then much safer to use and much more flexible to use as well.
Hi, is this the first step towards a Scala VM where you divorce completely from Java and have fully reified generics?
I'm not a fan of reified generics, just to say. I think reified generics in a VM is a mistake, and I think the .NET people found that out. The problem is that in a VM, if you have a VM, you have to keep things very stable. And a VM, also in a VM, you want to be able to be a backend for many languages. So the problem with reified generics is always you have to burn the type system into your VM. And as long as there's no universally agreed on concept of what this common type system should be, that's just premature. And I don't believe we will arrive at that over the next 20 years. So I think maybe in 20 years it will be time to do that. But for a VM, well, I think I think I don't really see the point of it because there are perfectly good VMs out there. You will get, in effect, something like a platform, so an interoperability format, an interchange format, and it will use essentially other VMs as the runtime. But it will be sort of one level above your typical notion of VM. I don't really see the necessity to take this and go down to hardware. There is some work, very initial stages on having an LLVM backend, and that then you could maybe call a Scala VM that you say, well, you have a lower level VM that you map to and do that. But it's way too early to tell whether that will be successful or to bet on that.
So did your tree format actually require a special syntax to do with macros, or was that just something you implicitly figure out from the basic tree format? You mean to execute macros? Yeah. No, that sort of falls out because the tree format simply says where we want to have a complete way to express what Scala is, and macros are nothing but Scala code, right? So of course, that means that what we need, if you have an interpreter for this tree format, then by definition we have an interpreter for macros, because macros are just essentially Scala code that we have in that tree format. So the reason I'm asking, of course, is that we've talked about source compatibility and binary compatibility, and really fear tree incompatibility next.
Oh, yeah. There's no silver bullet. That's right. Wherever you are, you
you will have some trade-offs with compatibility. I have some hopes that the situation will be relatively much more stable than in the other extremes.
You probably would also be able to optimize between. It'll probably enable optimization when you compile, let's say, to a single jar. You'll be able to strip unused code and maybe inline even code from other libraries.
Yes.
Optimize a lot more than you can within this.
Indeed, yeah, that's right. A lot of optimizations like this are actually already being done on the Scala.js, which relies a lot of them, both because you absolutely have to minimize code. You can't ship multi-megabyte JavaScript files, and secondly, because actually it turns out that the JavaScript VMs optimize quite a bit less than hotspots, so essentially you have to do more in the front end. But a lot of these things have been pioneered and have been shown to work very well on the JavaScript side. So just to give you a thing, that in the JavaScript benchmarks, there are actually quite a few benchmarks in the standard benchmark suites where Scala.js is faster than native JavaScript because it can do these optimizations.
Martin, thanks for the great talk. Actually, I was going to follow up on Yuri's question. So you mentioned JVM and JS are two backends. So you mentioned one kind of benefit Scala.js will derive from this. Are there any other implications for Scala.js or Scala on other platforms rather than JVM? So what other things could do? What other platforms could do with these trees?
What other platforms can? Well, it's sort of. Well, one thing you can do, for instance, is to say, let's say you want to do a Scala-specific code coverage tool. What you can do is you can write this tool once, have it work on the trees, and it will work automatically on JS as well as Java. So that's a big win, just to give you one example. You can have more and more things that both in the libraries, of course, you can publish for and be platform agnostic, but you can also have tooling that is platform agnostic, and that way that should make it more interesting.
How much of the compilation time is currently in the front end versus the back end?
It's currently about 40% front end, 60% back end. But that is, so in the current Scala C compiler, what happens, so as you've seen, the backend has a lot of phases that transform these trees. So essentially there's a lot of tree transformation going on. And the trees have types until we go into bytecode, Java bytecode or JavaScript. So there is this big issue to say, well, how do we maintain the types in the trees? Very, very early on in Java at the 1.x thing, we have said, well, every transformation has essentially to compute the correct types in the trees that it generates. It turned out that this was completely unmanageable. There were way too many things could go wrong. So in the Scala 2x series, what we did is essentially we ran the type checker over the generated trees. So you generate a tree, and the type checker runs over it, and it won't retype check the trees that you got from the previous phase, but everything new that you generate, the type checker will run over it. So that gives you sort of this weird relationship where you say most of the code is, most of the time is actually spent in the type checker, but it's also in the backend because it's the type checker running in the backend, essentially recompiling these transformed trees. And the trees become bigger and bigger. So in current Scala C, the trees become very big because every closure becomes an inner class, and a class is much bigger than a function. So that will be fixed in 2.12 when we go into lambdas, so we don't generate these classes anymore. But there are also other things that essentially everything you do just makes the code bigger. So the trees become bigger, and so the compiler has more to do, the type checker has more to do to type check them. So in Dotty, what we're going to do is we have this very simple type assigner, which essentially can recompute the type without running a full type checker. Because it turns out that a lot of the things that you do for the type checking, you don't need to do anymore. So it would be unreasonable, let's say, that you compute trees that rely on overloading resolution or implicit search. You could say, well, you should be specific in the tree that you generate here. So you don't need to do that. So that means that hopefully you will spend a lot less time type checking because you will have a lot less work to do. But I can't give you the numbers yet because the .NET compiler is full with instrumentation code, and we haven't really done any serious performance measurements yet. We have to rip out the instrumentation first. Good.
Any more?
Oh, okay.
Yeah, so since you've changed you separated the front end compilation, from the back end compilation that generate from the Scala tree, couldn't you basically have, you could have a pluggable surface syntax for Scala?
You could, yeah. Yeah, that definitely would make it easier. But we would sort of run into the same situation that, let's say, people have on the .NET platform. So if you have a very rich interchange format with the types and everything, then essentially what you can do is really having a different surface syntax, but the types would all be essentially the same. So it's sort of just different skins of the same. On .NET, people say, well, essentially, every language is essentially a C# in disguise because that's what the VM demands. And I think we would have a lot of maybe Scala dialects that could use the same thing, but there would be limits to what you can do, I think. But I think it would be interesting maybe for experimentation to say, well, that could actually become for sort of Scala-like languages, but you want to experiment, that could become a good platform in the future. No more questions? Well, thank you all for coming.